Okay, and so for our next talk, Federico will be telling us about proof-relevant models.
Thank you. This is a joint work with Axel, Kerinec, and Giulio Manzonetto from the Université Sorbonne Paris Nord. And so, if you consider a random paper on the denotational semantics of pure lambda calculus written in the 80s, it surely goes as follows. You have a Scott continuous model, D, and you want to study the theory generated by this model. The theory is the equational theory generated by the equalities of interpretation of lambda terms given in the Scott model, and it is called a lambda theory. Now, in order to do so, you prove the soundness of your model, meaning that the model preserves the reduction steps of your lambda terms, and then, using some magic, you are able to prove an approximation theorem that states that you can reconstruct the interpretation of your term by the interpretation of its finite approximation. Its finite approximation being truncation of its Böhm tree that is some kind of infinitary normal form of your term. Now, the magic that you use is state computability, so an impredicative technique, and then this allows you to prove that the theory generated by equality of Böhm tree is contained in the theory of your considered model. Now, if you want a complete characterization of your theory, you need to do some extra work, introducing some kind of complicated technical machinery, and then maybe you get that the theory of your model, for instance, is the same as the one generated by equality of Böhm trees, or maybe some extensional version of Böhm trees, such as Nakajima trees. Now, if we switch from Scott semantics to the relational semantics that was studied starting from the early 2000s, we can actually bypass the magic of state computability with a much more direct argument that passes from soundness to the approximation theorem, but just by the means of a simple induction. Still, though, if we want a complete characterization of the equational theory generated by the model, we need a lot of indirect, complicated technical machinery. And what we did in our paper is that if we pass from this standard categorical viewpoint of denotational semantics to a bicategorical one, so we perform a step of categorification, we actually can achieve the characterization of theories of model in a much more direct way as a corollary of approximation theorem. In particular, the soundness property of the model is now more informative, since the interpretation of lambda terms are now not just equal up to reduction, but they are actually isomorphic. So we have a non-trivial interpretation of the execution of a program inside of the model itself. From this, we get an approximation theorem, and the bicategorical structure of our model allows us to finally get a full characterization of the equational theory of our model in a very direct way as a corollary of the approximation theorem. Now, to be more precise about denotational semantics, Scott semantics consists of seeing a program as a Scott continuous map between two domains. And so the idea is that the program is seen as a function that can be thought as a black box that takes some input and then does something and gives you some expected output. But quantitative semantics inspired by linear logic can refine a bit the situation in the sense that you can also obtain quantitative information about the computation process of your program. In particular, the relational semantics, so the interpretation given in the category of sets and relation, it's the most famous kind of quantitative semantics. In particular, it allows us to have precise information on the number of steps to termination of your program, for instance, also the amount of resources used during computation, and in the non-deterministic setting, you can also count the different ways that your program gives you the output. Both Scott semantics and the relational semantics can be actually presented in a syntactic way, exploiting a particular kind of type system that are rooted in the notion of intersection types. Now, intersection types were first introduced by Koppe design in the 80s as an extension of simply typed lambda calculus, where we had this intersection constructor, KR intersection constructor, K can be also 0. And in general, the idea being that if a program is both typable with type A and B, should be typable with intersection type A intersection B. The intersection can be and should normally be at least associative and commutative, can be idempotent, and these intersection types are very powerful. In particular, can be used to present several denotational semantics. For instance, the family of models called filter models that are a particular case of Scott semantics are presented by the means of an idempotent intersection type. And we have also a notion of subtypings for our type system. Then the graph models that are simpler version of filter models that do not have subtyping, but still they can be defined as some kind of Scott semantics, still have the idempotency of the intersection types. And in the relational case, we'll drop both idempotency and subtyping, being the semantics quantitative. And so we can distinguish, we can actually count how many times we are using our input. For this reason, we don't have idempotency of the intersection. In all this framework, the interpretation of the program can be described in a very simple way as just the sets of the typing of the program in the appropriate intersection type system. So the pairs of context gamma and A under which your program is typable. And this is preserved under reduction. Now, intersection types are very powerful, and they are strongly connected with the notion of normalization. They can characterize several notions of normalization. In particular, they are closely related to the notion of Böhm trees. So a Böhm tree can be thought of as an infinite normal form that is introduced to give normal forms also to terms that are computationally meaningful, but they may not terminate in a standard sense of the reduction of lambda calculus. For instance, the most important example are fixed point combinators. And so the Böhm tree of a term should be thought of as a way to collect the full execution of your term that could be potentially infinite. And if the term is not normalizable, meaning that it doesn't ever produce stable output, stable partial output, it's going to be not computationally meaningful. And for this reason, we say that the Böhm tree of the term is going to be this bottom element. Otherwise, your program at some point is going to produce a stable result that is partial. And so we collect it as a node of our Böhm tree. And then we proceed by defining the Böhm tree of the inputs. The construction is coinductive, and the Böhm tree can be eventually infinite, as in the case of the fixed point operator, that we get just this infinite application of a variable to itself. There is also an inductive presentation of Böhm trees as a join of what are called the finite approximations of a lambda term. And finite approximations should be thought of as a finite truncation of this possible infinite tree. And they are defined by you just stop at some point of your tree and you put a bottom at the end. And for instance, just bottom is a finite approximation. Then you have, for instance, this is another finite approximation, then again and again and again. And they all approximate this tree that can be seen then as a join of the finite approximation. In particular, Böhm trees induce a very simple equational theory of lambda calculus that says two terms are equal if and only if they have the same Böhm tree. And in some sense, they characterize the non-extensional computational behavior of the programs, because we do not consider eta expansion with Böhm trees, but the beta structure is completely characterized by the Böhm tree. Now, we can link Böhm trees with relational models in a very strong way. And in particular, if we consider the notion of relational graph model, we can prove that in some cases, the theory induced by this model is exactly the same as the one induced by equality of Böhm trees. And relational graph models are a quantitative version of the standard graph models introduced by Engler, and they are a very simple structure. We have a set U and then an injection that should be thought of as a way to say that U is actually a set of types. Okay, so we can embed arrow types inside U itself, and the idea goes as follows. We have this kind of intersection types where the intersection connective is given by finite multisets over U, and indeed MF of U means finite multisets over U. And then we take an element of U, A, and we just say that when we have this pairing, we see it as a proper arrow type. And this presentation is very useful in the study of the model. Now, the interpretation of the term itself is going to be, if we see it as a characteristic function, it's going to be a test of typability. So it takes a context delta and a type A that are defined in U, and then it returns 1 if M is typeable in an appropriate system, or 0 otherwise. And this is very nice and well, and it has been widely studied and applied, but it's a bit unsatisfactory because it doesn't tell you anything about type derivations. And type derivation is the most important thing while we study our type programs, and indeed we can extract very important information from the derivations, and so to fix this limitation, we can perform what is called a categorification process. So we replace set theoretic notions with category theoretic ones. For instance, we replace sets with categories, functions with functors, equations with eventually natural isomorphisms, and then relations with the notion of distributor or profunctors. And in this way, we can pass from the test of typability proof irrelevant semantics to a proof relevant one, where we actually have the whole information about type derivations in our system. So the distributor semantics will take a context delta and a type A will return all the type derivation of your term up under this context with this type. In particular, the semantic is going to be two-dimensional in the sense that now we have a way to give a non-trivial interpretation of the reduction itself, of the computation step itself. So we have a way to categorically talk of the computation of lambda terms. And in this way, we can also categorify the notion of relational graph model. We have a corresponding notion of categorified graph model. And we replace sets with small categories, and then we have full embeddings of small categories. And again, the full embeddings gives you a way to talk about the category D as a category of types. And in particular, the arrow type is defined as follows. On the left, you are going to have these intersection types that now, instead of being a multiset, is going to be a list. So it's going to be associative, but not commutative nor idempotent intersection types. So it's much more explicit structure. And then again, the arrow type is given by the pairing. In particular, this list lives in the category, in a appropriate category of lists, that for the ones of you that knows a little bit category theory is the free monodial strict completion over D. And morphisms between these types should be thought of as allowable operations on this kind of bag of resources. And in our case, the only possible operations are actually symmetries, so we can have permutation, and in this way, we can retrieve the commutativity of the intersection types. Now it's explicit. Before it was just by equality. Now we can present a very explicit information about the permutation we are doing. But being our model quantitative, we cannot copy or delete, for instance, the elements in an intersection type. We have our categories of types. We can build an intersection type system to study the semantics induced by these categories. And in particular, this system is going to talk about this notion of categorical subtyping, where the subtyping is given by this idea of operations. And we have that subtyping is incorporated in each possible rule. And the most important rule being the application, where we see our program as a function that calls your input k times with potentially k different types. So you need to give to the program the input with possibly k different derivation of the input with type with the appropriate type. And then you have to do a concatenation of the context, and eventually, if you have a subtyping, you can also replace this concatenated context with the appropriate type delta. From this system, we can give a presentation of our semantics. In particular, we are passing from relation that we can see them as functions from Cartesian product of cells to the two elements semi-ring of Booleans to distributors, where we replace sets with small categories and then bool with the whole category of sets. In this way, the denotation of our term is going to be a distributor that takes finally a context delta in a type A, all living in our categorified graph model D, and returns all the type and derivation of your term under this context delta with this type. So now the semantic is proof relevant and gives us all the information that we wanted, and we are going to exploit it to study the computational behavior of our program. In particular, we can prove soundness that now it's just a definition of an interpretation of the beta reduction step inside of the model itself. And this beta reduction should be thought of a particular reduction over the type derivation that lives in the semantics of our programs. And in particular, we can prove properties about the reduction inside of the categorical model itself. So we prove strong normalization, that is, the reduction consisting of contracting typed redexes inside of the derivations is terminating always. And in particular, the proof of strong normalization is very easy because our system is quantitative. We cannot ever have a copy or deleting of our resources. And in this way, we improve it by just a very simple induction. And then we also get confluence as a corollary of the fact of lambda calculus itself is confluent. And then we use a general coherence result by Fioren-Saville to prove that two parallel reduction steps inside of the semantic itself are going to be equal. So it degenerated to a relation. And now we have this notion of normalization and reduction of the semantics itself. We can define a normal form of the semantics that always exists. And we prove that this normal form of the semantics of a term is the same as the semantics of its Böhm tree, that should be thought of as a colimit of the semantics of these finite truncations. And then we have a bicategorical version of the approximation theorem that talks about the execution of your program. It's a big step execution, if you want, because it consists these natural isomorphisms between the semantics of M and its normal form consists of taking a type derivation in the semantics of M and you just send it to its normal form. And we can start to see why proofs are relevant in our setting is because they allow us to do something that we couldn't do in the standard one-dimensional case. For instance, already in the relational semantics, if you take a finite approximation of M, you can actually build an element of the semantics of M. But instead, if you take an element of the semantics of M, you couldn't ever build in an easy way a finite approximant. Now, since we have that the semantics talks about type derivations, and the type derivation has a very strong information, we can reconstruct a finite approximant from the type derivation itself. So the type derivation, there are going to be some redexes that are not typed, and there you put a bottom, and you just get a finite approximation of your term. And thanks to this, we have that we prove the characterization of the theory of our model as a corollary of the approximation theorem. And in particular, first we have to define what is a theory for a bicategorical model. That is, the setting is much subtler than in the first dimensional case. So we have to equate terms up to isomorphism, but we can actually choose canonical isomorphism. We are not obliged to consider all the possible isomorphism. And in our case, we actually restrict the choice of isomorphism to the ones that are coherent with beta normalization of type derivations, meaning that the isomorphism is going to preserve the normal forms of the type derivations. Just beta normalization and not also eta expansion. And in this way, the theory generated by this isomorphism, we call it a non-extensional theory, because immediately discards the choice of isomorphism induced by eta expansion. In this way, we can prove that for all categorified graph models, even the extensional one, the non-extensional theory generated by them is the same as the one generated by Böhm trees. So I want to stress this fact that we are able to eventually define theories that depends on choice of isomorphism. In particular, if the categorified graph model is non-extensional itself, in that way, all the possible isomorphisms are exactly the ones that are coherent with beta normalization, because it couldn't ever validate eta expansion, being a non-extensional model. Now, I will conclude by talking a little bit about future perspectives. The first one would be so we studied a particular case of where we consider this notion of two-dimensional lambda theory. It would be nice to have a general categorical theory of these two-dimensional lambda theories, since you have this idea that you can have different notion of theories, like non-extensional, one-extensional, or whatever you want, depending on a choice of interesting structural isomorphism. And an important subproblem of this is to understand better the extensional case, since we actually restricted ourselves to a non-extensional one. Then it would be nice also to consider models that arise from different notions of intersection types. In this case, we had intersection types where you cannot delete nor copy, but then you can also build others where you can copy and not delete, delete and not copy, or do both. I did this in my paper of Leaks 2021. And finally, it would be nice to look at Abramsky implementation of domains in logical form from our two-dimensional perspective. Thank you.
Okay, we have some time for questions now. Over here.
So I have to admit, I'm a little surprised to see confluence fall out of this. You talk a lot about, the different normal forms and, this Böhm tree characterization of normal forms. And then, as an aside, confluence falls out of this. So I'm wondering, is the proof of confluence somehow, does it use a categorical inside, or is it just somehow contains the usual proof of confluence?
Yeah, so both actually, because the actual confluence result derives just by the confluence of lambda calculus, as we do it. But then there is another subtle thing that you want, that the reduction itself inside of the category should be a relation. So you should collapse all possible parallel reduction, and this is possible thanks to a general coherence theorem on Cartesian closed by categories that was proved by Fiore and Saville. This tells you that every two cells in the three Cartesian closed by category of error sets are equal. Okay.
Okay, so I had a question, which was, so the profunctor semantics that you have, it's the set of all typing derivations for the term. So that was very similar to this paper by Melier and Zauberger, where they use a functor as a type refinement system, and they have a similar setup where if you fix a term, you would get a profunctor of typing derivations over it. So I was wondering if you're aware of this.
Yeah, I'm well aware of this, and yeah, it's strongly connected. But in this case, you get this soundness result that is not directly available in their case, because their case is more general, and it's difficult to get this kind of invertible two cells that is actually induced by the particular structure of the model that I consider.
Okay. Well, if there's no more questions, then we'll have the next speaker set up, and thank you.